Hello there and welcome back. We are on to our next video about quantum physics, and today we're going to talk about wave functions for the most part. And today we're going to talk about wave functions. So in the last video we saw that that while waves can behave like particles, it turns out that also particles can behave like waves. And so this idea of matter waves helped us to explain things such as electron diffraction, like why electrons will behave like waves, for example, in like an electron microscope, and it can undergo the double slit experiment even though they are particles. But it also, matter waves also helps us understand atomic orbitals. Now, atomic orbitals is something we touched on earlier when we talked about like Bohr diagrams and that sort of thing. But it's also probably something you've learned a fair amount about, hopefully, in your chemistry courses, where we've got these different energy levels that our electrons exist at. So we already know that that Bohr said, okay, so electrons can only exist at defined energy levels, at the first, the second, the third energy level, and so on. And so what he said was, okay, if matter can behave as waves, then maybe the reason electrons can only exist at those discrete, specific energy levels, and the reason he thought that was happening was that the electrons were behaving as standing waves. Now, if we've got electrons behaving as waves around a nucleus, then maybe those are oscillating like standing waves. Now, you got a picture of a standing wave here on the side here. Just a reminder, on our standing wave, we've got nodes, which are areas where the wave is not moving very much at all. There is no amplitude, and there are antinodes where we see a maximum amount of amplitude. So stable electron orbits only occur when the circumference of the standing wave corresponds to an integer number of wavelengths. Now let's see what we mean by that. You can see in this diagram here, in this picture, I've got a set number of wavelengths, and my standing wave kind of is complete. It's a complete integer number of wavelengths. Here is a standing wave around a wavelength, but it is a non-integer number. You can see it doesn't quite line up in such a way to make that nice standing wave. If I was to just click this over, you can see that if I have an integer of 1, my standing wave is very simple. As I go up to higher and higher numbers of waves, I'm going to find that it doesn't quite line up until I get to exactly 2. And I keep on this process that as I go, my standing waves don't line up until I hit exactly 3. And now I can fit exact integer numbers of standing waves inside this orbital. And so when Bohr did that, what he sort of realized was I could have standing waves that kind of look like this, where that's my first energy level, and that is one complete wave. Or I could have standing waves like this, where I fit 2 complete waves in an energy level, or 3 complete waves, and 4 complete waves, and so on. And now, while again, this is a two-dimensional representation of what's actually happening, it did kind of pan out. It does seem like the electrons are kind of existing in these standing wave formations, okay? And so as I go to higher and higher energy levels, I'm just fitting one more wave into that energy level. Okay, so what does this mean in terms of electrons? Well, if we want to describe particles on a small scale, we know that they are going to behave as waves. And in order to describe them, because they're waves, they're not single particles existing in a single place in time like little marbles like maybe we thought of them before. And so since they are actually waves, they can exist in more than one place. They can exist as a series of probabilities. So their properties such as speed and position must be described probabilistically. Which is to say, we can never really know exactly everything about the particle. We can have a pretty good idea. We can have a safe bet that the particle is going to be found in a certain region of space, but we might not know exactly where it is. And this is all captured by something called the wave function. Now, wave function gets the symbol psi. And essentially a particle, the wave function of the particle describes its speed and position and perhaps other properties about it. And it does this in terms of probability. So when I have a wave function, it literally is a function that describes how my particle is behaving. Now, one of the things about the wave function is if you take the absolute value of the square of the wave function, this is going to tell you the probability of finding the particle in space. So the likelihood of finding a particle in a certain space. Okay, so you can see here I've got an example of a wave function, and my units on the y-axis are just, they haven't defined them, they're just some relative number presumably, and then you can see the x-axis is measured in nanometers. So this might be an electron's probability density in terms of its location from the nucleus, or maybe it's just some other particle that's described by this function. So where is the particle most likely to be found? Well, remember that the absolute value of the square of the wave function is our probability density. And so wherever this function, wherever the absolute value of the square would be greatest, is where I'd be most likely to be found. And you can see that happens here at x equal to 3. Now, that is not a guarantee that you're going to find our particle at exactly x equal to 3. In fact, it's not even all that likely to be at exactly 3, but the most likely place to find it is right there. You can see that the peak value is in that range. And so you can think, if it helps, you can think about the area under this curve as being kind of related to how likely you are to find a particle within a certain region. If you wanted to know how likely it was to find the particle between, say, 2 and 4, you can see that that's very, very likely. That captures most of the area. And there's a slim chance you might find it between 4 and 5, right? Okay. So this brings us to electron orbitals. Now, electrons exist in electron orbitals surrounding atoms, and so they exist at discrete energy levels. Okay, they have to exist at really specific points. They can be at 1 or 2, but they can't be at 1.5. Well, it turns out that these energy levels are what we call orbitals. And again, hopefully you've learned a bit about this in chemistry class. And that these energy levels, they're not absolute, but the wave function describes the probability of finding particles in that particular energy level in that space. And so this explains the shape of atomic orbitals. Now, you may have learned in other classes that there are, for example, 1s, 2s, 3s orbitals. And there are 2p, 3p orbitals, and so on. There are d orbitals and f orbitals. And you can see a little picture of them on the side. We're not going to dig too deep into that, but maybe we'll just think about the simplest, or the geometrically simplest orbitals, which is the s orbitals. So 1s, 2s, 3s. And you can see them here drawn in the first column of the periodic table. So I've got a probability density versus distance from the nucleus graph here, and it's showing the probability density of the 1s, the 2s, and the 3s. Now, there's a few features I just want you to notice. So think about what it means. What do these peaks mean? So what is the peak? What does that represent? And that is just simply the most likely location. It is not a guarantee. For example, is it possible that an electron in the 1s orbital be further from the nucleus than in the 2s? Absolutely. Take a look. You could have an electron all the way over here in the 1s, and maybe in the 2s it's actually very close. However, what does the area represent? So the area under these curves is going to be related to the likelihood of finding the particle in that space. You can see the 1s, most of the areas in that space, whereas the 2s, there's a little bit there, and then most of the areas in this space. You can see that on average, electrons in the 2s orbital, at the higher energy level orbital, are further away from the nucleus, and that's why they're at a higher energy, because on average, they're found further away. Now, the last thing I want to point out, which is kind of sneaky, it's down here at the bottom. You can see there are a few regions here that where my 1s touches the x-axis, and then for the 3s it touches it in 2 spots, right? And so what happens right there, where essentially my phi squared equals 0. What is that saying? Well, those are regions in space where the electrons cannot exist. If they're in the 2s orbital, there's a little space there it can't be in. And same thing with the 3s. Well, those spaces correspond with the nodes of my standing waves. So you can see, for example, that the 1s orbital has no nodes because it's just a single wave, but the 2s orbital has a node and the 3s orbital has 2 nodes, and you can imagine the 4s orbital has an additional node and so on. So these locations here where I cross the x-axis are areas of 0 probability density, okay, where we cannot find the electron. All right, the last thing we need to talk about, which is a bit of a side note, is something called stimulated emission of radiation. Now this is a little bit of a callback to atomic energy levels, but it's a particular case that we see come up. So when you have light of a specific frequency that is absorbed, it might cause electrons to move to a higher energy level. Now, that photon gets absorbed and the electron jumps up to a higher energy level. All good. Now, what can happen is that that electron doesn't want to stay at that higher energy level, so it could spontaneously fall back down by undergoing what's called spontaneous emission, which is to say it could just emit a photon or a series of photons that get it back down to its ground state. Now, when it does that somewhat randomly, and it's just going to produce a photon that's going to go shooting off in some random direction of some random phase and so on, okay? However, if we were to, before that electron manages to drop down, okay, if you were to hit that electron with a second photon with the exact same frequency that it needs, then it's going to drop back down and emit an identical second photon, okay? So you can see here, absorption happens when we absorb a photon, and then emission happens when it just falls back down. But if while the electron is still in that excited state, you hit it with the same photon that originally got it there, then when it drops down, it's going to give off 2 identical photons. And what's special about this is they're going to have the same frequency, obviously, because it corresponds to the same energy level drop, but they're also going to have the same phase and they're going to have the same direction. So what that means is we can create a whole series of photons that all have the same phase, frequency, they're all headed in the same direction. And what that gets us is super awesome. That gets us lasers, okay? And lasers are great for a bunch of reasons. In fact, laser stands for light amplified by stimulated emission of radiation. And so it's a particular way that we can get light kind of all cohesive. All right, that is it for our lesson on wave functions.